Hello, my name is Tessa, and for today's lab, we are going to be talking about modeling chirality and cycloalkanes, starting with chirality. So I have here two models made with a modeling kit similar to the one that you probably have at home. This is going to be for practice exercise 1, so please do follow along with the text. Feel free to stop this video as necessary in order to build your models or read through the text. Models that are chiral are by definition non-identical mirror images of each other. So this is really important to be able to see with a modeling kit like this because on paper it might not make as much sense as it does in person. So I have here two different models made of the two identical structures that they have shown in the first practice exercise. If we look at them from a couple of different angles and imagining that this line right here is our mirror, you can see that these are both mirror images of each other. Now, if I take these two, which I have already noted are identical despite being mirrors of each other, and I rotate them to place them side by side, you should be able to see that they are in fact identical to each other in structure and position. If, however, I take one of these hydrogens on the same carbon as the OH group and replace it with something different, in this case, a bromine, do the same thing on the other, leaving them as mirror images. Once again, these are mirror images along this line. However, you might be able to see already that they are not quite identical. One of the ways that you can prove this to yourself is if you leave one and you try to rotate it to make it the same by putting this bromine on this side, you should be able to see that now your oxygen, your OH group, is no longer in the correct place to make them identical. There is no way for you to now rotate, flip, or otherwise move this molecule without breaking any bonds to get it back to being identical to this one. Thus, while they are mirror images, they are no longer superimposable and are no longer identical, meaning that they are chiral. Please feel free to build the models of these two compounds and demonstrate this for yourself, taking the time to look it over, rotate it, and try to make them look the same. One of the easiest ways to check whether a molecule is chiral is to look for an internal mirror plane of symmetry. There are several examples here for the second practice exercise, which asks you to build the three structures and look for the internal plane of symmetry that's shown as drawn on the paper. This is the third example made in a model to demonstrate that there is no mirror plane and to show exactly what this dashed and wedge bond mean on a structure like this. So I made a 6-membered carbon ring as the base using these black circles. And then on just these two, I added the fluorines in the opposite sides to each other as represented by the dash and the wedge. And then just for the ease of comparison, added the hydrogen to these two. Keep in mind that there are hydrogens on these other carbons as well, but I have neglected them just for simplicity. So you should be able to see that there is no mirror plane here. You can't put your hand at any point along the molecule and do a mirror image and still be able to get the same thing. You also, if you flip it, cannot get it to be the same as its mirror image if you were able to imagine the mirror image on the other side of this. Sticking with this model, I'm going to demonstrate the concept of determining R and S at tetrahedral stereocenters. The first thing that we want to do is find one of our tetrahedral stereocenters. As an example, I am going to use this carbon. The very first thing that we want to do to determine whether it is R or S is assign a CIP priority to each of the group bonded to the stereocenter. The highest priority group is labeled as 1 and the lowest is 4. There is a demonstration of this as well in the lab manual for this experiment. So what we would determine here, assuming that green is a very heavy molecule with a high atomic number, something like fluorine, for example, hydrogen is going to be our number 4 priority. This green one will be our number 1 priority. This carbon here will be number 2, based on the two things that are attached to it, the fact that it has this other green one attached to it. And this will be our number 3. We want to make sure that our lowest priority group, our number 4 hydrogen, is going to be in the back from what we're viewing. So we want to put it behind the carbon so that we can no longer really see it. We then want to keep in mind 1, 2, 3, and figure out whether this is a clockwise or counterclockwise rotation when counting. So if we go 1, 2, 3, that's counterclockwise, which would mean that this would be an S stereocenter. The steps in determining whether a planar stereocenter is E or Z is similar to the method for determining whether a tetrahedral stereocenter is R or S. The very first step is determining and assigning our CIP priority to the two groups bonded to each carbon of the alkene. Instead of counting from 1 to 4, we're just going to worry about which one has the lower priority and which one has the higher priority on each carbon. So, for example, here I have the 2 white hydrogens attached, and I have 2 bigger things. It's not necessarily important what they are at the moment, just that they are bigger than hydrogen. So hydrogen is going to be our number 2 on each of these carbons because it is the lower priority, while these colored ones will be the higher priority. So, for example, 1, 2, 1, 2. If both of your number 1 priorities are on the same side, it is Z for cis. If they are on opposite sides, it would be E for trans. Keep in mind that molecules that have a double bond in the center cannot freely rotate around that bond. As demonstrated by this model, I cannot rotate it. That is why it matters whether these two are on the same side or opposite sides. Enantiomers are an extension of the idea of chirality that we've already discussed. Enantiomers arise when you have molecules that have multiple stereocenters. For an example, I have built a model of a compound that is also shown in the lab manual. One of the things that you can see here is that we have several different groups, but we only have 2 tetrahedral stereocenters. Keep in mind that in most places I've neglected the additional hydrogens that would be on some of these carbons, for example, for clarity. These 2 carbons here are our tetrahedral stereocenters. Currently, both of them would be drawn as wedges due to the fact that they are coming out from the plane of the rest of the molecule towards us, the viewer. However, if we were to change both of these stereocenters to be away from us, the viewer, this compound is no longer identical to the previous compound. Please feel free to rotate it and mess with the model as you have built. in order to see that this is true. Because we changed both stereocenters, this would be considered the enantiomer of our previous compound. However, what if we only changed one of our stereocenters? This molecule is no longer identical to either the first or the second version that we had made. When we change only one of the stereocenters, leaving the other the same, it is not an enantiomer of our first structure, but now instead a diastereomer. So I have demonstrated 2 enantiomers and 1 diastereomer. See if you can try to come up with the 4th structure. An additional case that you might have is a molecule that has asymmetric carbons, but because of an internal plane of mirror symmetry, there can be achiral forms of it. This is an example of a molecule which has 2 different tetrahedral stereocenters, this carbon and this carbon, since they are attached to 4 different things at each carbon. However, because of this mirror plane here, this molecule, as made at this moment, is overall achiral due to that mirror plane. If we were to change the connectivity, it could make another achiral molecule, which would in fact be identical to this molecule, or we could make a form that does have chirality. As it's connected now, this molecule is chiral overall, as well as having 2 tetrahedral stereocenters. Again, if you build this model for yourself and attempt to rotate it and make them identical, you should be able to see that when we make both of these OH groups line up with each other, our carbons are no longer the same, thus making this a overall chiral molecule. Molecules which have a mirror plane that causes them to overall be achiral despite the presence of tetrahedral stereocenters are called Meso compounds. Now we're going to talk about how to model cyclic compounds. You may have noticed earlier when I had a cyclic compound that not all of my carbons in the ring were exactly aligned with each other to make a flat compound. Cyclic rings like this do in fact not make flat compounds. They make something called a chair conformation, which is what we're going to be talking about how to model and how to see before you have to actually draw these chair conformations. Once you've built the model, you should be able to look down your carbons and see that, like this carbon, for example, they're most likely eclipsed entirely. In order to get to the chair conformation, we want to make sure that every single one of our carbons is staggered. The first thing that we can do to help us reach this staggered chair conformation is to find carbons 1 and 4 and move one of them up and one of them down. So if we start here and assign this as carbon 1, then this becomes carbon 4. I'm going to choose to move this one up and this one down. We should now pretty naturally reach a chair conformation. However, the way that we can check and kind of adjust our molecule is to go ahead and look down each of these bonds and just make sure that they are, in fact, staggered. Go ahead and take a moment to double check that each of your bonds is staggered properly. At this point, you should have a proper chair configuration. There's a couple of things that I would like to point out that will help make sense of the drawings of chair configurations, as well as what they actually mean in space. One of the things that you might notice when looking at this model is that you have 6 different hydrogens or substituents, depending on what is on your ring, pointing up or down. 3 of them pointing up and 3 of them pointing down. These are going to be called axial. You'll also notice that we have 6 different hydrogens that are kind of off to the side, though they also alternate kind of towards a upward position and a downward position relative to each other. These are going to be called equatorial. Take a moment to compare what our model looks like and these axial and equatorial hydrogens to a properly drawn chair configuration on page 97 of the manual. Once how that drawing is put together makes some sense to you, we can look at the side of the molecule, and you should be able to see, generally speaking, how our Newman projection is going to look. Again, also on page 97 of the manual, with this carbon being slightly downwards, this carbon in the back slightly upwards, and then these sets of carbons front to back. Chair conformations are not the only conformation that exists for a 6-membered ring. There is also the boat and twist boat configurations. Images of how these are drawn are shown on page 98 of your manual. Instead of having 1 and 4, one of them being up and one being down, a boat configuration is going to be the situation where they are both upwards. You can see that these hydrogens here begin to interact with each other in what is called a flagpole interaction. You can begin to see our boat conformation. Once you have your boat conformation, there is another conformation that exists called a twist boat conformation, which we can get to from this particular conformation. The way that we do that is we look at these 2 hydrogens that have the flagpole interaction, and if we just slightly twist them in opposite directions, we will get to a twist boat conformation. Be careful not to continue twisting these, because as you do, you may be able to see that we developed just another boat conformation. Understanding cyclic compounds takes a lot of practice. Please make sure to take the time to look at this model with different substituents, along with the different drawings of chair, boat, and twist boat conformations, particularly with an emphasis on the chair conformation. You should be able to understand each of the equatorial and axial positions on the chair conformation, as well as the difference between the drawings of the chair conformations when you go through a chair flip. Do practice flipping the chair on both the model and in your drawings, as it will help you later on in the course. Additionally, when replacing these hydrogens with larger substituents, take a look at the potential interactions that might occur, particularly when you have large substituents in either an axial or an equatorial position. When looking at that and the When looking at those larger substituents on the axial and equatorial positions, do keep in mind what a Newman projection of these might look like and what sort of interactions might be happening between different substituents on different carbons. Don't forget that organic chemistry takes a lot of practice. So make sure to take the time with your models and the different exercises in your manual along with this video to help practice a lot of the different concepts with conformations and chirality in particular, to help you understand these so that when you see them on a piece of paper, you can visualize them better in your head and understand more about why we care about these different conformations and what they affect in actual chemical reactions.